Hello all. We will discuss today about the buck converter and especially how to select the LC filter components. So let's start. For our buck example, we used data from our previous video with a linear regulator example. Therefore, we assume that we have, let's say, a battery car as the input voltage and an electronic circuit in the car that needs to be supplied with 5 volts and consumes 2 amps. So we define the input voltage nominal as being 12 volt. We can also define a range in the 8 to 16 volt. As I said, we want output voltage 5 volts and we will have a 2 amps. At the output, we select the switching frequency as being 100 kilohertz. We want to have an inductor current ripple of 40% of the output current, of the maximum output current, and this inductor current ripple will be valid for the nominal input voltage. We want to have a maximum output voltage ripple within 100 millivolts, and we know that our load generate transients like 1 amp with the speed of 1 amp per microseconds, and for these transients we don't want to see a voltage deviation which is higher than 250 millivolts. Okay, therefore let's go for our buck converter. First, about the operating states, we will consider continuous conduction mode of operation and steady state. We have actually two states during on time of the MOSFET. Actually, the energy is taken from the input voltage source, goes to the inductor and to the output capacitor and load, which is not represented here, and the current goes back on the ground return path back to the input voltage source. For the off time, actually, because we build up some current in the, or we have in the continuous conduction mode current all the time in the inductor. Therefore, we have energy, and we know that the inductor tries to preserve the current circulation. Therefore, we can look at this inductor as a current source, so it will push further the current in this direction to the output capacitor load, and then it will the current will find a path to this freewheeling diode and will close the circuit back. Okay, so we have two states. In order to get the ratio of the duty cycle, or the DC transfer function as it is often called, we need to apply the inductor volt second balance principle over one switching period. So actually, this is what I put here. Maybe let me 1 second to get the laser pointer. Okay, good. So this is what I put it here. So during on time, we have the voltage over the inductor as being input voltage minus output voltage. And during off time, we have the output voltage, assuming that we have ideal components. So on the off time, this diode will conduct. So if it is ideal, we don't have any voltage drop over it. This point is tied to ground. Of course, here during on time, we have a polarity with plus on the left side and minus on the right side. On the off time, we have plus on the right side and minus on the left side. However, applying this inductor voltage second balance, we know that over one switching period, the average inductor voltage must be 0. Therefore, the two parts must be equal. Okay, we know that the duty cycle, we use this identity duty cycle as being on time over switching period. Then we can rewrite the equation, and then by simple algebra manipulation, we can extract the duty cycle or the DC transfer function as being output voltage over the input voltage. Okay, now the LC filter. For the inductor, the things are pretty easy. We need to select one of the states, either on state or off state of the MOSFET. And here I simply use the on state. We have the voltage. and then the on time is simply a duty cycle over switching frequency and the imposed current ripple we want to have. And this is the way how we immediately get the value for the inductance. For the capacitor, we need to consider at least 3 points. One is the output voltage ripple requirement we have. Second, we need to look for the RMS current to be sure that the selected capacitance can handle the RMS current. And third, we need to consider also the step load requirement in conjunction, you'll see, with the selected cutoff frequency. So that we will be able to stay within the acceptable voltage deviation during those transients. So in the end, the chosen capacitance must satisfy um, all aspects at the same time. Okay, let's now take one by one and see what we can say about it. So for output voltage requirement, at the beginning, I considered an ideal capacitor. So no parasitic elements for the capacitor. That means the entire voltage ripple will have only a capacitive contribution. Okay, I did a very simple buck schematic in a simulation circuit to um, check the relevant waveform. So I plotted here the relevant waveforms for what we need to know in order to, in the end, to find out the value for the output capacitor. Okay, so in red we have the current through the inductor. In cyan we have the current to the load resistance. So we see that we have an average current to the load resistance of 2 amps, and then the current in the inductor is going from 1.6 amps to 2.4 and back. So we have the 0.8 amps current ripple as we imposed. Then I plotted the current through the capacitor. What we can immediately observe is that the current through the capacitor has exactly the same shape as the current through the inductor, but without any DC bias component. So the current in the inductor has a DC bias, which is actually the load current. Yeah. Okay. Now we need to understand that. I mean, we see that the inductor current goes above and below the average output current. So when it is above um, the output, the load current, that means we have a current that will go into the capacitor. So we are pushing some electric charge in the capacitor. The effect, of course, will be that the voltage will rise. It has this resonant fashion, but will rise. So I colored in blue this region where the inductor current is higher than the output current. So this voltage variation here is actually what we called the ripple, is the peak-to-peak ripple voltage, and is this delta VC. So we have imposed in our design data a maximum of 100 millivolts for this delta VC. Therefore, in the end, in order to calculate the needed capacitance that will give this voltage ripple for the inductor current ripple we have, we need to calculate the amount of charge we have here, the amount of charge we push into the capacitor. Well, in order to do this, I construct this rectangle ABCD, and by geometrically looking at this figure, we can say that the amount of charge is actually half of the rectangle area. So let's calculate then the rectangle area. Of course, we know that this charge variation, if you want, we have in the capacitor is equal with capacitance times the voltage variation, and this is especially the identity we will use to extract the needed capacitance value. Okay, so let's calculate the this delta QC. We know it's half of the rectangle area, so we have 1/2 times, and now rectangle area would be just the product of, let's say, CD times AD. The CD we know, we see it's just half of the inductor current ripple, because we have the same current ripple to the capacitor, yeah, without the DC bias. So it's actually half of this. So we have delta IL over 2. And then for the AD, what we realize is that actually we have half of the on time plus half of the off time. And this is what I put here. So we have 1/2 times on time plus off time, which is switching period. So in the end, this charge variation in the capacitor is given by the inductor current ripple over 8 times switching frequency. So now by using the identity above, we can directly extract the value needed for the capacitance. Again, this is for the ideal case, so we have only the capacitance contribution. And let's now go to the simulation program. So I set up a very simple simulation to verify this points. Okay, let's have the grid as well. And go into the steady state. Okay, something like this. Okay, so what we see is that the inductor current goes from 1.6 to 2.4. We have the current through the load, which is average 2 amps, and the current in the output capacitor, which goes from minus 400 amps to 400 milliamps to 400 milliamps and back. Okay, and now for the output voltage, we can simply put a cursor and use the built-in measurement functions like peak to peak. And then you see we have just slightly above 100 millivolts, so we have 100.5 millivolts. So this is what I would expect. For the value of C1 capacitor, I just use this parameter, which is C out, and it is defined here. Is the same formula as you saw it in the presentation. The two behavioral voltage sources here used are just to confirm me the values. So we have 10 microvolt, but we know is 10 microfarads for the output capacitance, and this is the value of the inductance, the calculated value for the inductance, 36.46 microhenry, we know. Okay, then let's go back here. Of course, real capacitors have parasitic elements like equivalent series resistance and equivalent series inductance. Usually the inductance is, if it's in the range of nanohenries, the contribution of the ESL is very small to the total output voltage ripple and can be easily neglected. And therefore, well, the previously derived equation or formula can be adapted or updated with the contribution of the other parts. Of course, now if we said the ESL part is going to be neglected, then for the ESR is just a discussion based on the type of the capacitor it is used. So if we use ceramic capacitors, those are having normally low ESR values, so probably the capacitance contribution in the total ripple will be significant. On the contrary, if we use electrolytic capacitors, those are having higher ESR values, and we can have this part as being dominant, or at least can be comparable on the same order of magnitude, the two parts. So someone can decide to let's say if we have a 100 millivolts total allowable voltage ripple, someone can say, okay, I will use 50 millivolt for the capacitive part and 50 millivolt for the ESR part, and then we can simply recalculate our values. So the needed capacitance will be twice, so we will need 20 microfarads, and the ESR needs to be 62.5 milliohms or smaller than that. So 62.5 milliohms will give us a peak-to-peak voltage ripple, which will be 50 millivolts. Yeah. Okay. So now it's clear. We know that the capacitor introduces a phase shift between voltage and current, and that means the two parts will not peak at the same time. So in the end, this formula, it is a kind of a worst case formula, so it is a conservative one. But let's check this in a simulation. So we have a simulation right now, which I updated the capacitance value, and I introduce a series resistance with this 62.5 milliohms. I can run it. Okay, we can see again output voltage, current. Let's see the contribution of the capacitance by plotting this voltage. No, I don't need this one. Okay, we'll do it again. Sorry. Okay, this one. And then we want to see the contribution of the ESR itself. Okay. We will again go to the steady state. Okay, so the ESR contribution, we have it here. Yeah, we can use the same peak to peak, and you see we have close to 50, so 49 millivolt is the contribution. So it's close to 50 millivolts what we said. Maybe I should do a bit of a zoom. Okay, then for the capacitive part, we'll use the same, and for the capacitive part, we have again 49 millivolts. So close to the 50 millivolts we just said to do the split. And now if we look for the output voltage, the peak to peak is not 100 millivolt, but it's only 62 millivolt. The reason is that the voltage over the capacitor has a peak which is not coincident with the voltage peak over the resistor. Yeah, that's what I wanted to say with the phase shift. So the combination, so the sum of those two waveforms is actually in AC is actually what we see right here. So that's the reason why we don't have 100 millivolts and we have only 62 millivolt peak to peak. Okay, let's go back. Okay, for the RMS current, we need to be sure that our capacitor can handle the current. So because we see there is a rectangular or triangular waveform, sorry, there are already calculated formulas or provided formulas that can be used, or in this matter we can calculate the RMS current to the capacitor, but I am strongly recommending, or yeah, if you have a simulation, just look for the RMS value over the simulation, and that's it. I mean, we have here 0.2319, so 232 millivolts, milliamps RMS. Sorry, that's the RMS current through the inductor, so it's much easier. Nevertheless, you can still use those kind of formulas. Okay, then for the stepped load requirement, it's about the we need to consider also the cutoff frequency of the open loop. We know that, for instance, there is a rule of thumb for analog designs. The cutoff frequency should be smaller or equal with switching frequency over 10, so 1 decade below. For digital designs is even lower, so is maximum switching frequency over 20. The reason here is the phase erosion mechanism, but we will discuss later on this. Okay, so for our buck converter, we will target a cutoff frequency of 10 kilohertz, and then we will use the approximation which is presented by Christophe Bassot in his book Switch Mode Power Supply Spice Simulations and Practical Designs, and he's saying that the closed loop output impedance of the converter is approximated by the output capacitor impedance at the crossover frequency. So actually, we said our load introduced a change in output current of 1 amp, and then with this formula we end up with a value of like close to 64 microfarads we need. So much larger value than we previously calculated, like 10 micro or 20 micro. And this approximation, Bassot is saying that is valid only in continuous conduction mode, and only as long as ESR is less than the reactance of the capacitance at the cutoff frequency. So we can calculate or see what would be the maximum ESR we can accommodate from this perspective in order to to have a valid condition for the for our calculation. So in this case, it's 250 milliohms. Okay, now we will look for some ceramic capacitors. So I searched on Murata website. I found a 22 microfarads, 25 volt rated X7S. This is dielectric in a 1210 package. They have an online tool that provides all the important characteristics. So for the ESR, for the frequency compensation, the value of the ESR at cutoff frequency is of importance. For the ripple, the value of the ESR at the switching frequency is of importance. So we have like 5 milliohm and 3 milliohms, and of course there are different D ratings in the capacitance with applied DC voltage over the capacitor. There are some temperature contribution as well, and I was also looking for the maximum allowable current depending on the frequency and what temperature rise will give. We know that we have like 0.2 something amps RMS, so only one single capacitor will handle the entire RMS current. So from this perspective, we are totally covered. Okay, so applying all those dependency, we end up with worst case capacitance value of 17.5 microfarads. Therefore, in order to have the 60 something microfarads, we would need 4 parallel capacitors. So for 4 parallel capacitors, we'll have a value of about 70 microfarads. So I updated the simulation in this case, and of course now you can see we have a much higher capacitance. So we have 17.5 with 3 milliohms, and this M equals 4 instruct the simulation program that we have 4 capacitors in parallel. Now the inductance, I put it in clear, 36.46 micro henries, the value, and I only have the duty as a parameter, like V out over V in. Okay, we can add window here and check the Okay, let's take this and put it here. And in steady state, we are in this condition. So let's try here a peak to peak, which is only 16, 17 millivolts. So we have a much higher output capacitance than we initially calculated. Okay, that's it for today. Thank you for watching. Bye.